Alright, so we're going to go ahead and get started here on section 6.5. I'm going to record this video a little differently just because the section is a little bit different. We're talking about modeling data, so hopefully you've got the note sheet in front of you. And we'll start over here on the right. We're talking about modeling using different kinds of models beyond just linear models, and primarily we'll be looking at exponential models as an alternative, but really looking at linear versus nonlinear especially. So let's talk about some vocabulary first. Alright, so first thing that we will ask when we give you some data, if the data has any sort of pattern at all, we will ask you whether it's about its direction, whether it's positive or negative. So the kind of the sample data that I have over here is positive because it's going up from left to right. You can think of it in terms of a positive slope. So it's going, as you move from left to right, it's going up. All right. Now, it could also obviously be going down, and so if it was going down, then you would see points that were kind of falling. All right. And they don't. This data falls pretty much on pretty close to a line, but it does not have to be the case. So it could be any type of data that is has sort of a pattern. Okay. So positive or negative is the first thing. The next thing is whether it's linear or nonlinear. So this data, as I mentioned, looks pretty linear, right? I mean, it looks pretty much like it's pretty close to a line. You could draw a line of best fit in there and it would fall very close to the points. All right, but you might have data that does something like this. Let's get rid of that. So, maybe you have data that comes down like this and it looks like exponential decay. Like maybe you're looking at the temperature of a hot drink that you just warmed up out of the microwave or something, and you check the temperature every couple of minutes and you see that it's going to fall in this kind of pattern. That would be non-linear. Okay, so it's basically just data that doesn't look like a line. The last thing is we will ask you about the strength of the data, whether it's weak, strong, or there's no correlation. So if the points cluster around the line of best fit or the curve of best fit, then there's a strong correlation. If they don't, if they're quite scattered, then there's a weak correlation. So like if you can see a pattern, but it's not very tight, then it's a weak correlation. And if there's no pattern at all, it's just a cluster of dots and data points, then there's no correlation. Okay, so that sort of covers the data, the vocabulary, at least at the beginning here. So in this first question, we've already sort of answered it here, but it's saying what is the direction, form, and strength of the data. So I'm going to try and write with my cursor here. We'll see how this goes. So first of all, the direction is positive. Okay. Not very good. Okay, so the direction is positive. The form is linear, so it definitely looks like a line. So we've got linear. All right, and then the strength of the data. This is a strong correlation. It's very closely packed dots there along a line of best fit, so it is a strong correlation. Okay, so several of the questions just ask you this: look at the data. Is it correlated positively or negatively? Is it linear or nonlinear? And then is it strong, weak, or no correlation? Okay, so that, let's see if we can just let's do this. There we go. All right, next, let's do an example here. So Sahara is selling cups of lemonade as a fundraiser. She records the grams of lemon powder she uses to make a cup of lemonade and the time it takes to sell the lemonade. Her data set is that. Graph the data and describe its form and direction. Okay, so my graph is not going to look great. I'm going to use Desmos over here. You'll notice at the top of the page this link, bit.ly/regression tool. And that will take you to this Desmos graph here. This Desmos graph has a data table, and then it has a linear regression, and let's go like this. So it has linear regression on the left here, so that's the first regression. Then it has exponential regression, and then there's some other ones in here as well. So we're not going to talk a lot about these, just only briefly, but there's a quadratic regression to make a quadratic, like a parabola, a logarithmic regression to make, if your data looks like it's a logarithmic function, and then power regression will give you a power function, so something like 7x to the 5th power or something like that. We're not going to use these very much. Like I said, we'll only talk about them briefly. But what you can do with this is you can put your data in here, right, your x's and y's, and then you can just turn on the linear regression and turn on the exponential regression and compare them. Okay, so let's first get our data into the table here. So we'll clear out. I put in 2 data points just so those little yellow or orange caution things wouldn't show up there when you landed on the page. But anyway, here we go. So we've got 0. I'm going to put in the x-coordinates first. So 0, 1, 2, and then if it's a pattern, then Desmos will automatically fill it. We want to go out to 5. Okay, and then in the y's, we're going to go, let's see, 0.05, 0.1, 0.2, 0.4, 0.8, and 1.6. And there's a good chance that the scale, the default scale, is not going to be great. So you will have to change that. You can either do the zooming thing here. This looks, zooming is going to work pretty well. Or you might have to change it, you know, the x and the y-axis scales here. So this looks like nonlinear data, just kind of looking at it. I think a line of best fit, you could obviously draw a line of best fit, but I think this data is curving up into the right here. So just, I know it doesn't ask us this, but like, so you can see that this data is going positive. So it's positive, it's nonlinear, okay, because it's starting to curve, and then it's a pretty strong correlation. So, you know, given the choice between linear and exponential regression, this looks like it's going to turn and become exponential. So let's take a look at our regressions here. So get out of that. So the way these regressions work is it will compute a line for you. So here's the line that it computed. It says the slope of this line is 0.28, so that's the m. And then the b, the y-intercept, would be negative 0.19. Okay, so you could graph this line with this slope and this y-intercept, and it would graph the same red line. Okay, so that's how you get the linear regression. This r value is really important. This tells you how strong the correlation is. All right, this is called the correlation coefficient. And the correlation coefficient, if it's very close to 1, then that means a very strong positive correlation. If it's very close to -1, it's a strong negative correlation. So basically you want it close to 1 or -1, depending on the data. Closer to 0 or 0 means no correlation at all. Right, that might be worth writing off to the side somewhere on your notes. All right, so like I said, this looks more exponential. Let's take a look here. So look at how well the exponential graph follows the purple dots. The line is not bad, but you can, so the line is not bad, but you can see that that exponential curve fits it really well. Down here, for the exponential regression, you can see you've got A is 0.05, so that's the number out in front, and that B is 2, okay? And you have to turn on log mode. I should have set that as the default, but if you turn on log mode, it will also give you an R value for your exponential. So you can see that the R value here for the line is pretty good. It's 0.9. But here, the R value is exactly 1 for exponential. That tells us that the exponential curve, or the exponential model, is the best model to fit the data. Okay, so that's going to be our model. So it says, and so you'd want to plot those points, and then it says, oh, I guess it did ask for the direction, form, and strength. So yeah, the direction, I'm not going to try and write with my cursor, I already mentioned it, but just to be clear, again, direction positive, form nonlinear, strength very strong, given the R value here. Don't forget to turn on that log mode so that you can see the R value. Okay, so that's how you set up the regression tool. Let's go on to the next problem here. It says Frederick has 20 weeks to train for 15K race. He tracks his progress every week in the table below. Use regressions to determine the best model, then determine if he'll be able to complete the 15K in 20 weeks. How far will he be able to run? Okay, so I already typed this in to save us some time. So here's what the data looks like. And so you see I use the regression tool. I typed it in off to the left here. And so here's what I'm going to do. I'm going to run the line, or plot the line, and see the R values here at 0.87. Hold on. R value is at 0.87 or 0.88. So that's pretty good. We'll turn on the exponential regression. Get rid of the line for a second. Turn on log mode so we can see the R values and compare them. You can see the R value for the line's a little bit better. 0.87 or 0.88. This is 0.85. So just a little bit better for the line. So we will go with the linear regression here as our model. Okay, and then it says use this model to make a prediction. How far, determine if he'll be able to complete the 15K in 20 weeks. So let's check. We would need to look at the graph of this. So here's how we're going to graph this. I'm going to go here, I'll hit enter. Let's actually plot the line so we can use it, I guess is what I'm trying to say. So y equals, actually maybe we can, yeah, actually, so we can just trace. Maybe that's the easiest way, but you could also just plot it too. So y equals, actually, let's not, sorry, I'm like thinking out loud here. Let's just trace here. So we want to know if in 20 weeks, which remember that's on the x-axis for this, so the x-axis is weeks. Okay, so we want to know if after 20 weeks, Frederick can run this 15K. So let's go out to 20 weeks, and you can see at 20, looks like it's 4.886, and yeah, he's not going to be able to complete it. You can see he's just not going to go far enough. Then the next question is, well, okay, how far will he be able to run? So you can see he can, at 20, he'll be able to go 4.8 kilometers, 4.9 kilometers. So the answer to that one is almost 5 kilometers. So again, you can write that down. I'll spare you the drawing with my, or writing with my cursor here. But anyway, no, he won't be able to run 15K in 20 weeks. And how far will he be able to actually run? Well, it's right there at 4.9 kilometers. Okay. All right, let's move on here. Possible types of regression. So there are three types, or there's several types of regression, as already mentioned. Linear, exponential, logarithmic, quadratic, and power. Okay, so I already showed you those off to the side in Desmos here. You can see here there's graphs of them. So let's blow this up a little bit. Here's what the graphs look like. All right, there is, you can see this is obviously a line. Here's what a quadratic looks like. It's, well, it looks like a quadratic function, right? A parabola. Exponential and logarithmic, that's the ones we'll deal with the most, is exponential especially. What looks like exponential, or logarithmic would look something more like this. Okay, and I should use a different color. Logarithmic would look more like this. All right, and then the last one is power. We will not deal with power very much. Quadratic is a type of power function, but anyway, we're not going to deal with that too much. We will ask questions like this, though, so let's clear this. We will ask questions like this one over here. It says identify the type of regression in each of the following equations. And so these, you're just going to graph the equation, and you're going to see what the regression, what type of regression would fit it. All right, most of the time, these are just equations that look just like the regression. So 2 times 3 to the x, look, that's an exponential function. Okay, so what's the type of regression for that one? Well, it's exponential. Okay, how about 2x to the third power? Well, when you come over here and you graph 2x to the third power, you can see that that's going to be a power function. And if you can't see that, you can see it's not going to match any of these, right? So it's because it's a cubic function, so that would be a power function. So that would be power. All right, and then the last one here is x squared plus 3x plus 7. I'm not even sure that we need to graph that. It clearly fits this format. Whoa. It clearly fits the format of a quadratic here. And if you graph that, you'll get a parabola. So this is definitely a quadratic. Okay. Quadratic. And that's it. So that's sort of just a surface level approach, or surface level understanding of different types of regressions. Remember that this tool will be really useful for you since you're using Desmos primarily. If you want the graphing, how to do this in the graphing calculator, you can take a look at Mrs. Pepper's videos. Those are linked in Classroom as well. But otherwise, that wraps up the modeling section here.